Hello everyone. In this video I want to talk about all things covalent compounds. Covalent compounds, covalent bonds. Again, anytime we have a covalent thing, it makes something called a molecule. Okay, so covalent compounds are also known as molecules. Okay, so notice we didn't talk about that when we talked about ionic things. So with covalent compounds, there's a couple different types of covalent compounds. Of course, we have molecules, which was what I just mentioned. But I probably should take back what I said. Most of the, I won't take it back actually, but most of the things we'll talk about will be molecules, okay? But there are some things called covalent network solids, which are based off of covalent bonds, but we don't necessarily call them molecules. Okay, these are larger compounds consisting of repeating elemental or molecular units all covalently bonded together, such as a diamond, which we'll see pictures of in a little bit, and of course silicon dioxide, in other words, beach sand or quartz, or any a number of different types of quartz. Okay, there's not only quartz, but there's also um, different versions of that. So, okay, so anyway, I think we're looking at a couple different versions here. So diamond versus graphite. When we take a look at diamond versus graphite, these are examples of covalent network solids, okay? In other words, a repeating unit over and over and over again, but the repeating unit this time is a carbon, okay? They basically take, they're called allotropes, which means they take different forms. So carbon looks like this is diamond. So this is actually diamond right here, okay? And diamond forms what's called a repeating tetrahedral pattern, okay? And we'll take a look at that as we move on in this chapter. However, graphite is repeating, carbon is repeating, but in different ways. Notice it forms these hexagonal patterns, okay? And this forms a flat sheet here, which is bonded to with something called pi bonds to another flat sheet, which is pi bonded. Again, these pi bonds, these vertical lines I'm drawing here, are very weak actually. And we have this flat sheet right here. And when you write with graphite, these sheets get sloughed off. These sheets get removed, and that's what actually comes off on your pencil lead when we have graphite. Pure graphite versus like a number 1 versus a number 4 pencil or something like that. It has to do with how much clay is made in there, or clay is mixed in there, excuse me. So the situation with covalent bondings, let's go back to the collision theory. So again, two atoms have to approach each other, but in this case with covalent bonding, they don't have enough energy to take away electrons from each other, so they're going to share instead. And now we have this idea behind attraction versus repulsion. So if they're really attracted to each other, the carbon atoms, like for example, if we have two carbon atoms, the bond length looks like this because they're attracted to each other, okay? However, if we have a carbon and an oxygen, it might be a little shorter because now the oxygen wants to bring in that carbon a little bit tighter, okay? And we'll talk about bond length more when we talk about the different forms of bonds, multiple bonds, different things being attracted to each other. So again, the bond length, the bond between any two nonmetals, um, is a balance between attraction and repulsion. Okay. Now this is typical graph here. So where we see a balance between two different atoms. So actually, you look at this from left to right. Excuse me, from right to left. You have two atoms that are quite far apart from each other, and they are not attracted to each other at all. So there's zero potential energy because they're just not attracted to each other. The moment they do get close enough together, now we see this attraction. Notice it's negative because it's exothermic. So we see it on the negative side here of our graph. And now here they bump into each other. There's the collision theory again. When they bond and they eventually form this bond between a perfect attraction versus overlapping up here where they're repelling each other, we establish a bond. The bond actually has two things. It has a certain amount of energy, which is down here, and look at this, very exothermic, at least this one's exothermic, and we have a length, okay? So how long they are and how much energy it takes to break them, okay? Two things you can glean from this graph, okay? So make sure you know this graph. The characteristics of covalent bonds, they do occur between two nonmetals. The electronegativity differences are very close, if not identical. So electrons are shared. They're not transferred like they would be transferred in ionic bonds. If we have something that's unequally shared, we call that a polar covalent bond. If the electrons are equally shared, we call it a nonpolar covalent bond. Weak attractions between molecules. So two cellular units called molecules are really not very strongly attracted to another molecule or other molecules around it, especially of the same type. But the attraction between atoms within the molecule is quite strong. As a matter of fact, it's the stronger between the two. The covalent bond is stronger than an ionic bond. Okay, so we'll rank that here in a second. They do have quite low melting points and boiling points because of the weak intermolecular forces between molecules. They can form all forms of matter, solid, liquids, and gases, or all three. And they are electrically non-conductive. Whether they're dissolved or molten, they will not conduct electric current. They are generally non-electrolytes. Okay? So check this out. Pause when you need to. There's the answer. There you go. And here we are. Next one. Okay, so this is an ionic bond here. Okay, this is an ionic substance. This is covalent. Okay, this is actually a salt, and this is actually sugar. Table salt and table sugar. Okay, so we're going to rank these. The strongest bonds are these little ones. I think you can see my red drawing here. Those are covalent bonds. Those are the actual covalent bonds. Okay, covalent bonds are within a molecule. Those are number one. Those are the strongest. Okay. The second strongest are bonds between ions. Three-dimensional, X, Y, Z directions, whatever. Those are number two. Okay. Now those are the two chemical bonds we study in chemistry. Okay. So there's a third attraction, and that's the attraction over here on the right between molecules. So anytime we have an attraction, we're going to draw it as a dashed line, not a solid line. Solid lines are for bonds. Dashed lines are for attractions. Those are called intermolecular forces, and those are way, way weaker, hundreds of times weaker, and we call those number three. Those would be ranked number third as far as bonds, or I shouldn't call them a bond, but again, strength of attraction goes. So the covalent bonds inside of a sugar molecule are number one. The ionic bonds between ions are number two. And the attraction between molecules is number three. Okay, so we've already looked at this already. Okay, so I'm not going to beat this up too much more. So again, we do know what electronegativity is. It's the ability of an atom to attract a pair of electrons in a bond. Again, I'm yelling at you again. Okay. The idea here is that there is a gradient. You can see the electronegativity values here. Ionic would be, again, these are differences. When I subtract the two electronegativities that are listed somewhere on the test or somewhere in your homework, you see we do have a continuum or a gradient here. Okay. So compounds are never 100% ionic, even though I categorize, hey, this is ionic, this is a polar covalent, this is nonpolar. It's really not that way, guys. So even though I'll categorize something as ionic, look how close it is to being polar covalent. So even the strongest ionic bonds will have some covalent character. I'll talk about this more in class, but rarely do electrons. It's almost impossible to think that electron will only stay with the atom that it's designated to. They do jump back and forth. So there is a little bit of sharing even in the best ionic bonds. Okay? And there's also some bunching called, which leads to something called London dispersion forces. You've seen this already. Electronegativity values increase to the right and up any period, or along a period or up a group. Here's a polar covalent bond. You'll notice this picture does a nice job of showing how the electrons like to be around the oxygen more than they like to be around the hydrogen. This makes this slightly negative and this side slightly positive. Now, why is this side slightly negative? It's not ionic, guys. It's just the essence or the feeling of being negative. And the reason is because the electrons are mostly around the oxygen. So if the electrons are mostly around the oxygen, that means they're not around the hydrogen, which makes that side slightly positive. Okay? Why is it positive? Don't forget there's a proton in here. Okay? So this is a polar covalent bond. Here's another look at it, using something called a dipole moment. I've seen them drawn different ways. Basically, it always points to the more electronegative atom, and the cross stands for the positive or electropositive portion of that bond or molecule. Okay, check this out. Here's the answer. We'll talk about this in class. Another question. Answer. Okay, again, you can check this out. Again, I'll talk about this in class a little bit more, but now we're moving into this idea behind symmetry, polarity, electronegativity values. It all kind of goes along with this, okay? So check out this slide, but when we talk about whether we determine something as a polar or not, first of all, we got to look at the bonds. Then we got to look at how the bonds are arranged. Then we got to look at and that has to do with what's called the symmetry. Is it, can you split it down the middle? Is it bisectable? And again, the bottom point is to be a polar molecule, you must be asymmetrical to ensure unequal distribution of electrons. So again, we'll talk more about that in class as we move through here. And I'm going to wait on this now. That'll be the next video. So if you have any questions, go ahead and ask.